So now that we've performed the coding to figure out the temperature profile of this heat diffusion equation, we want to perform a Van Neumann sensitivity analysis to figure out why it is that R has to be greater than or equal to 1/2 for the graphs to work. So to do that, first we're going to look at an actual answer of this heat diffusion equation, which scholars have figured out. And so one of these answers is the temperature is equal to e to the I k delta x, or I is some imaginary number, times e to the negative alpha k squared t. And so what we're going to do is take the derivative of this equation with respect to x and t, and first we're just going to plug them in and make sure that it actually is a valid solution. So the first derivative of temperature with respect to position is going to be equal to ik e to the ik delta x times e to the negative alpha k squared t. And we only bring down this ik because this term right here is going to be a constant because t is not changing in this derivative. So the next step is to take the second derivative with respect to x. And this we're going to end up with an I squared, which we know is going to be equal to -1. So I'm just going to put a negative there. And then we're going to have k squared from this k that comes down. And then it's going to be e to the ik delta x, e to the negative alpha k squared t. So this is going to be our expression for the second derivative of temperature as it relates to x. Now we're going to take the derivative of temperature as it relates to time. So to do that, now this first e to the I k delta x is going to be constant. So I'm going to start by just writing that in. And then we're going to bring down the constants from this one, which is negative alpha k squared. And then add in the rest. So this is going to be our derivative of temperature as it relates to time. And as you can see from this equation, if you add an alpha in here, these are going to be equal to each other. I'm not going to write it out because everything will just cancel. But if you multiply this times alpha, it'll be exactly this. And so now that we know this is a valid answer, we're going to perform the Van Neumann sensitivity analysis. So now that we've proved this to be a valid answer for the differential equation we solved, we're going to plug these t values into the expression that we coded for to figure out what about this expression puts a limit on r. So the first thing to do that is to plug in tj comma n into this equation. So that gives us e to the I k j delta x e to the negative alpha k squared in t. And the j goes in the first one because it scales with delta x, and the n goes in the second one because it scales with t. So the next step is to do the same thing but with j plus 1. tj plus 1 n is equal to e I k j plus 1 delta x e negative alpha k squared in t. And so because this j plus 1 is in here, it's going to give us an extra e term, which I can bring out now. E to the I k delta x, e to the I k j delta x, e to the negative alpha k squared in t. So as you can see, these two terms are exactly equal to tj comma n. So I'm going to go ahead and substitute that in for those two terms. And that's going to be our value for tj plus 1 comma n. Now we're going to do the same thing for tj minus 1 comma n. So it's going to be e to the I k j minus 1 delta x e to the negative alpha k squared in t. And if you look at this, you can tell that it's going to do the exact same thing as the j plus 1, except it's going to have a negative I in the numerator. So it's going to be e to the negative I k delta x times t j n. So now that we have all of those expressions, we can plug it in here and simplify. t j n plus 1 equals r times e to the I k delta x t j n plus 1 minus 2r t j n plus e to the negative I k delta x t j n. And so now all of these terms have a t j n in them that we can factor out. So t j n r e to the I k delta x. And I'm going to go ahead and rearrange it to put the e's next to each other. Plus r e negative I k delta x plus 1 minus 2r. And so now what we're going to do is we're going to use something called Euler's formula to change these exponential functions into something that we can deal with a little more easily. So Euler's formula states e to the I k is equal to cosine, or e to the I x, rather, is equal to cosine of x plus I sine of x. And so e to the negative I x is equal to cosine x. Cosine is an even function, so it will stay positive. Whereas sine is an odd function, and it will go negative. So because we add these two together, you can see that if you add these together, the sine terms cancel out. So these two added together, we can say it's just going to be 2r cosine kx plus 1 minus 2r. And so this is very important because it gives us this cosine function, which will make it very easy to take the limit of the expression. So now that we've derived this equation, we can do a few manipulations to figure out how r affects the temperature. So as you can see here, if this term here is greater than 1, the temperature is going to always increase. So we want this term inside the parentheses, the absolute value of that to be less than or equal to 1. So I'm going to go ahead and write out negative 1 is less than or equal to 2r cosine k delta x plus 1 minus 2r is less than or equal to 1. And now what I'm going to do is I'm going to factor out this 2r. So that'll give me negative 1 is less than or equal to 2r times cosine k delta x minus 1 coming from that 2r, and then plus 1 coming from that plus 1. Less than or equal to 1 still. So the next step is to subtract 1 from every side. So that gives me negative 2 is less than or equal to 2r times cosine k delta x minus 1, which is less than or equal to 0. So because cosine k delta x will never be greater than 1, we know that cosine k delta x minus 1 has to be less than 0, or less than or equal to 0 rather. So this right side is always going to be true. So the only thing we need to worry about is this negative 2. Go ahead and erase this left side, or the right side. Now I'm going to divide everything to get r on its own on the right. So I'm going to divide first the negative across, so that gives me 1 over, and then because I divided the negative, this is going to switch around. 1 minus cosine k delta x. And I also got rid of the 2 by dividing by 2. And because we divided by a negative number, this the direction of the inequality is going to change. So that leaves us with 1 over 1 minus cosine kx is greater than or equal to r. And so this will give us a very good visual of how k affects r. So we want to figure out what is the largest value of r that can be determined by k. So again, because cosine cannot be greater than or equal to 1, we know that 1 minus cosine kx and because cosine k at delta x at its minimum can be -1, we know that the lower bound is 1 over 2. And that comes from 1 over 1 minus -1. And the maximum value of cosine without actually affecting, or without getting a divided by 0 error, would be 1 over 1. And so that is actually less stringent than this value right here, which means that this 1/2 is going to be the determining factor for our R. So this Neumann sensitivity analysis showed why in the code the graph cannot handle things when the R is less than 1/2.